Hello, YouTube. Welcome back. Today, we're going to go a little bit deep into cryptography, although this, is not as deep as maybe we will go next time. But this is going to be a quick intro into cryptography, not necessarily web security or anything like that. This is cryptography, which means basically you're dealing, let's start with the goal here. So one thing that we can build from scratch is encryption. And you probably already know what that is, the problem setup. But the goal is to send a message from one person to the other. It could be over the internet or whatever. But you want to send a message to someone else, and if the message is intercepted by an adversary, then it's okay because it's encrypted. And so that is the ultimate goal here. With some message, can we encrypt it and send it to Bob, and then Bob can decrypt it. And if they have a shared key, then we're in business. So this is kind of a constrained problem. There's going to be so much work just to do something kind of simple, it seems like. They have to both have some shared key. And yeah, it seems kind of simple. But the point of cryptography, as I've learned, is to be able to build it from scratch. You're building up some building blocks that you can use elsewhere, but you're guaranteed things you need to guarantee by the laws of physics that something in math that this is secure, and that's what we're going to be doing basically. If you're coding Python, you would just have some function already that exists, I don't know, and you would pass in the message. But it's how do we absolutely guarantee by the laws of math that this is true and can be trusted? So we're going to build up encryption from scratch. So the way we're going to do that is, so this is our goal. A kind of an arbitrary message just turns into a ciphertext, which means the message is encrypted, and then Bob will decrypt it. So let's add some little bit of notation, and then we'll go to the roadmap. So let's turn this into math notation a little bit. So we have an encryption scheme, which has two functions, encrypt and decrypt. And so encrypt takes in a key and a message, and then outputs a ciphertext. And then decryption takes in the same key, takes in the ciphertext, and outputs the message. So Bob is doing this, Alice is doing this. Okay. And then we can talk about the message space, the key space, and the ciphertext space, and maybe we'll get into that later. But M is an element of this, the key is an element of this, and the ciphertext is an element of these. These are all sets. Okay, so that's a little bit of notation. And now let's turn to the roadmap. Okay, so first, the goal is to encrypt arbitrarily long messages. If you want to encrypt a big file or a code base or whatever it is, a sensitive text, you want to encrypt a long message. But first, we actually have to start with encrypting short messages. And when we talk about cryptography, people have definitions. There is a true definition of security. Well, there's actually two definitions of security. And the first one is called perfect security. So let's start with this one. Perfect security. This is basically, it's perfect. This is the goal, or not the goal. This is, ideally everything would be perfectly secure, but as we'll see, that's not actually the case. Okay, so here's one way to build perfect security. So we have this encryption. So this is one function, and then we'll basically just talk about a bunch of ways to build this one function. But the first way to build it is you take the key So first, you randomly sample a key, and then you do C equals the key XOR M. And this is meaning you randomly sample the key. Okay, so that is the first way to do encryption. In perfect security, the definition of perfect security is that if you have two messages that you encrypt, the distribution of all the possible ciphertexts is the same. And that's kind of confusing initially when I heard that. But basically, so if you take like a simple example, say like you have a message, like you have 0, you're only encrypting 1 bit. So you have the message, and then you have the ciphertext. This is like a table. And let's say this is like a table to how you would encrypt something. So you go like this. So the distribution, if you have just encrypted something, every message has one ciphertext, right? So the distribution is the same for either message. But if I did this, actually, that's okay. Yeah, so we need to be encrypting more bits to see what happens. Okay. So let's see. If we were gonna do something like this, yeah, I mean the distributions would not be the same, and this is not really what I want to focus on too much. Perfect security is basically just saying if you have the ability to have the keys as the same length as the message, then you can do a perfectly secure something with XOR. Okay, and if you have, okay, yeah, so like let's just move on from this. Okay, now let's define semantic security. Okay, so it's more interesting to define security in terms of games. So this is how a game is played, a security game. So this is how you draw and then okay. So you have the adversary and challenger. And the adversary will send 2 messages and then get a ciphertext back. And then it's up to the adversary to guess which message was encrypted. And so they'll make a guess, and then you call it B hat. And you want to know the probability that B hat equals 1 in experiment 0, meaning the 0 message was encrypted. And you also want to know the probability, same thing happening, and assuming in this world that the first message, the number 1 message was encrypted. And so like call this W0 and W1. And W0, this should be what is called negligible. So in perfect security, this equals 0. But we have to make some concessions and call it negligible instead. And so there's a real definition of negligible, but obviously it just means like super small number. And the idea is that it grows kind of exponentially small. Okay. Like something like this, I think. Okay. So now we have defined semantic security. So if something is semantically secure, then this is true. And this is kind of the definition of semantic security. So when you talk about encryption, you want it to be semantically secure. And this is one definition of security. We're going to make more as we go. Okay, so the goal is to encrypt long messages. What have we done? We have defined a way to be secure, and then we also have one way of actually encrypting something. And the problem with this way of encrypting something is that the key has to be super long. The key has to be the length of the key has to be equal to the length of the message, which is just not practical. So we need a way of using shorter keys. And okay, so maybe we would do something like this where we encrypt. So we have like the key that we always have, but maybe this is like a smaller key space. So keys are like 10 bits or something, and we wanted to encrypt 40 bits. So we would take the first 10 bits, encrypt, and then append that to the next 10 bits, and the next 10 bits, and so on. And this is going to cause lots of problems because we're using the same key to encrypt multiple times. So like, maybe we'll give an example using the security game. Actually, that might take too long. Okay, so I'm just going to tell you this is bad. This is bad right here. So we need a way to fix this. How can we have new keys every time without sampling new keys? Because if we just like had a new key, we also have to send it. Like Bob has to be aware of it, right? So every time you generate a new key, you're going to run into some logistical problems. So we need a way of generating new keys based on just one key. So let's call that function f. So we already have our one key, and then we want to input x, and then we want to be able to use this as our encryption key. So we want to put that in there and put the first part of the message. So we have like 10 bits. And then we can do it again. And again. So this thing is just going to be outputting randomness for us to use, which seems like kind of overpowered. Like, how do you even build something like that? But we're going to do that. And so just a flash forward, that is called a pseudo-random function, where you input something and it gives you something that's pseudo-random. And then you can use that to encrypt. So first, if we want to do PRFs, we have to do PRGs. And so to get a PRG, a pseudo-random generator takes this and outputs R, and this R is pseudo-random, but S is like, so you're just growing randomness, as they say. So what does this look like? So there's the discrete log problem, which says if you know a y, it is very hard. If you know a y and a g, it is very hard to go and find x. But we can give you one bit based on x, and that is our randomness. And that is not enough time to really understand what is going on there. I don't understand it as much as I would like to. But the idea is that you have some big prime number p, and you have a generator g of zp star, And then, so that looks like 1, 2, all the way to p minus 1. And you have some element there, like g to the 5. And that gives you a y. But then how do you know, if you have a y, very hard to find x. It's very hard to know what element in ZP it is. And so we're going to use the x's, so like x0, and that will give us x1, so then we'll go like this, and then, but then we're going to output some bit. And as soon as we can output some random bit, or pseudo-random bit, then we can get into business. So now that is the core primitive. This is like the atom of building pseudo-randomness. And so from there, say we have g of x0, then we get an r, basically we get an x1 and some random bit, some pseudo-random bit. And so this is enough, if we do it sequentially, to give you a different PRG that then gives you double the length. So you can go from n to 2n, and as soon as you have something doubling, so yeah, basically we went from s to s plus 1 bits, and then we can do that again and again and again and again and again until we get something that's s plus s, until we get to s plus s. And so then this is s to 2s, which is what we need to do the GGM tree. And that sounds cool. So from here, you can go S, and then you have, hold on. Okay, cool. So you start at the top, and then you just G of S, and you make a binary tree like this. And now all of the leaves are pseudo-random. And there's a big proof that you can do to guarantee this, but basically every step of the way, step 1, step 2, step 3, people have done proofs on, and you could take the time to do that. But the goal here is basically, right, we wanted to do f, k, x. And so the x is basically telling you which leaf you are, and if you have a huge tree, you can't even enumerate all of the leaves, then this is what gives you a pseudo-random function. Okay, so now that you have a pseudo-random function, you can do better encryption. And so we actually haven't really done any proofs in this, I realize, which maybe is like a crazy way to talk about cryptography. But basically every step of the way, there is a proof involved. But the point is that you're starting with a generator and a prime number, and then you're building it all up and guaranteeing this stuff using proofs. So you're like, so every step of the way is a new primitive, and then you're putting them together, and then you're proving that this is still secure under these definitions in a simplified manner. Okay. And so now we have a new way of encrypting. Instead of using the same key every time, we're going to pick one key. Alice and Bob are going to pick their one key. And then, okay. So same signature. Now, every time there's a new message, you're going to make an X. you're going to do this. Sorry. Yeah, okay. Like this, right? So before we had this key here, now we replace it with the output of the pseudorandom function. And when you put it this way, it's like it's not the most complicated thing. But the complicated thing is the algebra and the proofs, which I have sort of glossed over because I don't want to make this video crazy long. But that is kind of the story. I guess the point here, I wanted to start with the goal. Like, what is our goal here? And what is the story of how you get there? And I think the main story here is that you are building it up with many building blocks. You're proving things along the way, and then you're guaranteeing this idea, this like very concrete idea of security. Okay.